There is a metal cylinder sitting on the surface of Mars at this very moment. It is roughly the size of a piece of chalk. Inside it is a core of rock drilled from a formation the mission team gave the name Cheyava Falls, extracted in the summer of 2024. The rock has markings in it, small, dark, distributed through the sediment in ways the scientists on the team have described, using words like poppy seeds and leopard spots. On Earth, if you showed those patterns to a geobiologist and asked them what made them, they would reach for a specific answer almost immediately. They would tell you those are the kinds of patterns left behind by microbial life. They would tell you that combination of iron minerals in those particular arrangements in that kind of mudstone is what certain bacteria produce when they extract energy from their chemical surroundings. They would tell you it is, in the language of the field, a biosignature. Last year, after 12 months of careful internal review and external peer scrutiny, NASA's official position shifted to acknowledge what the team had found. The phrase they settled on was potential biosignature. The word potential is doing enormous work in that sentence. Nobody at NASA is saying life. Nobody is saying confirmed. The language is deliberate and precise, in the way that the language of scientists who understand the weight of what they might be looking at tends to be. But the cylinder is real. The rock inside it is real. The patterns are real. And the tube is still there, sitting on the surface of a planet that by the best current evidence lost its ability to support life somewhere around 3 billion years ago, waiting for a mission that by the current schedule will not retrieve it until the late 2030s at the earliest. Tonight, we are going to talk about that rock, but we are not going to stop there, because Mars is not the only world that has gone quiet. It may not even be an unusual one. What we are really going to do tonight is sit with a question that does not come up often in polite conversation, because the honest version of it tends to make people uncomfortable. We have now confirmed the existence of more than 6,000 worlds beyond our solar system. The working estimates for how many more exist in this galaxy alone run into the hundreds of billions. The instinct, the natural human instinct, is to look at those numbers and conclude that somewhere in all of that, someone must be home. The universe is too large, too old, too full of the right ingredients for the answer to be nothing. But the more carefully you look at what it actually takes to keep a world alive long enough for anything to matter, the more the story starts to shift. The story stops being about whether life can start. It starts being about whether life can last. Those are not the same question. They are not even close to the same question. By the time we are done tonight, you are going to look at the night sky differently, not as a place that is empty in the way a dark room is empty, as a place that may be very, very full of something quieter than we expected, something that ended, something whose light is still traveling toward us even though the source has long since gone dark. Here is where the standard conversation about this subject goes wrong. When people argue about whether anyone is out there, they tend to organize themselves around two positions. The first position holds that the universe is populated, that other civilizations exist or have existed, that we have simply not found them yet or have not been looking in the right way. The second position holds that the universe is empty, that we are alone, that the silence is the answer, and the answer is nothing. Those two camps have been arguing with each other for decades. The argument is real and the stakes are real, but both of them are missing a third possibility, and the third possibility is the one we are walking toward tonight. The third possibility is that the universe is neither empty nor populated in the way either camp imagines. The third possibility is that it is full of worlds where the conditions for life arrived, ran for some span of time, and then departed. Full of worlds where life may have begun and then stopped. Full of worlds with the porch light still burning and no one left inside. Before we go any further, if you are the kind of person who finds yourself awake at some unusual hour, thinking about questions like this, instead of something more practical, take a moment to like this video or subscribe to the channel. It costs you nothing, and it genuinely helps this reach more people who are also awake at unusual hours, thinking about the same things. That is the only ask. Now, let us get into it. The number to hold in your mind first is 6,087. That is the count of confirmed worlds outside our solar system as of January 2026, according to the NASA Exoplanet Archive, which is the official ledger where confirmed detections are recorded. NASA crossed the 6,000 threshold in September of 2025. To give that number some texture, there are roughly 195 sovereign nations on Earth. The number of confirmed worlds beyond our solar system exceeds that by a factor of more than 30. And those are only the ones we have actually managed to detect with instruments sensitive enough to register them. The real number, the estimated number, is in a different category entirely. There are approximately 200 billion stars in the Milky Way. The data gathered by NASA's Kepler mission and its successor, TESS, suggests that virtually every star hosts at least one planet. Many host several. When astronomers run the arithmetic, the resulting figure for the total number of planets in this galaxy alone sits in the hundreds of billions. Of those, the most recent estimates place the number orbiting within what is called the habitable zone, the region around a star where liquid water could in principle exist on a planetary surface somewhere in the tens of billions. Tens of billions of worlds where the conditions are not immediately ruled out. So the question becomes immediate and genuinely strange. Why is it so quiet? The first thing to understand is that the phrase habitable zone is, in its common usage, somewhat misleading. It does not mean that a planet within that zone has water. It does not mean it ever did. It does not mean the planet has an atmosphere capable of maintaining liquid water, or a surface temperature currently within the range liquid water requires, or any of the other conditions that the word habitable implies when we use it in ordinary conversation. It means only that the orbital distance from the star is roughly consistent with liquid water being possible under some set of idealized assumptions. The conditions could still be ruled out by any number of other factors, and very often are. Of the 6,000 confirmed exoplanets we currently have on record, the overwhelming majority are nothing like Earth. The first planets we found around other stars were hot Jupiters, enormous gas worlds orbiting so close to their stars that their upper atmospheres glow with reflected heat, some of them completing a full orbit in a matter of days. We found them first because they are the easiest to find. Their size and proximity to their stars make their signatures strong. Then came the super-Earths, rocky worlds significantly more massive than ours, many of them in orbits so tight that a year on their surface lasts a fraction of ours. Then came the tidally locked planets, worlds where the gravitational grip of their host star has slowed the planet's rotation until one hemisphere faces the star permanently while the other faces away permanently, leaving a sunlit side baked into bare stone and a dark side cold enough for the air itself to condense and fall as snow. When you look honestly at the catalogue of what we have found, the planets that resemble Earth in any meaningful combination of size, composition, orbital distance, and host star stability are rare. Out of 6,000 confirmed worlds, the number that could be described with any credibility as roughly Earth-sized, in roughly the right kind of orbit, around a roughly sun-like star, is in the low dozens. Most of what is out there is either too large, too hot, too cold, too close to a violent star, or too far from any star to matter. They are stones in space. They always were. But that is only part of the answer to the silence. The part that is harder to explain is not the worlds that could never have been alive. The part that is harder to explain is the worlds that by any reasonable statistical argument should have been alive or might have been, and from which we still hear nothing at all. The silence of the candidates. The silence of the planets that had what it takes. That is the silence worth sitting with. There is an image I keep returning to when I try to hold all of this in my head at once. Imagine a library. A large one, old, built with high ceilings and long rows of shelves that go back further than you can see from the entrance. You arrive at night. The main lights are off. Someone left a few of the emergency lights on near the exits, and you can see the shapes of the shelves and the spines of the books by that dim, scattered light. The library is not empty. You can see that much just from the entrance. The shelves are full. Every book on every shelf was written by a real person, printed with real ink, bound with real care. The library was not built empty. It was built to be full, and it is full. But it has been a long time since anyone came in. The card catalogue has not been updated. The return desk is unstaffed. The lamps that used to light the reading tables have burned out one by one, and nobody has replaced them. The books are still there. The voices that wrote them are not. That is the universe, as the evidence currently allows us to understand it. Not empty. Quiet in a different and more specific way. When the Kepler Space Telescope spent 9 years staring at a patch of sky containing roughly 150,000 stars, what it was actually measuring was the brightness of each of those stars over time, thousands of measurements per star per day, looking for a particular kind of dimming. The dimming it was looking for is what happens when a planet passes between the star and the telescope. The planet blocks a small fraction of the star's light. The star dims slightly. The dimming repeats on a regular schedule because the planet keeps orbiting and keeps crossing in front of the star on that same schedule. From that repeating shadow, astronomers can calculate the planet's size relative to its star, the length of its year, and how much energy it receives from its star. That is what most exoplanet science looks like at its foundation. You stand outside the library. You can infer from the shadows on the windows that there are shelves inside, that there are aisles and corners and rooms beyond rooms. You can estimate the number of books and their approximate dimensions. You cannot go inside, and you almost certainly cannot tell from the outside whether anyone is still in there reading them. There is another layer to the silence that is less about distance and more about timing. Even if every Earth-like planet in this galaxy had produced an intelligent civilization at some point in its history, the probability of any two such civilizations existing simultaneously, both in the window of their own history, where they are capable of and actively engaged in the kind of communication that could cross interstellar distances, is, when you do the math, quite small. Consider the timeline of our own world. Human radio technology has existed for roughly 100 years. Recognizable human civilization in any form has existed for perhaps 10,000. Our species, in its anatomically modern form, has been around for about 300,000 years. The Earth itself has been capable of supporting life for somewhere around 4 billion years. If you compress all of that habitable history into a single calendar year starting on January 1st, the entire span of human existence does not begin until the final 90 seconds before midnight on December 31st. The era of radio communication fits inside the final second. Now imagine a galaxy where every habitable world has its own version of that calendar. Each one started at a different point in galactic history, each one ending at a different point, most of the calendar on each world quiet and slow, with only a few seconds near the end where anything loud or detectable is happening. The probability of two of those calendars overlapping precisely in those few loud seconds is low. If you reached into the history of a random planet and pulled out a moment at random, you would almost certainly land in a long stretch of silence before the beginning, or after the end, or in the vast middle where nothing yet capable of making a signal had appeared. The silence we hear is not necessarily the silence of absence. It may be the silence of timing. The calendar on some of those worlds ended before ours began. The calendar on others has not started yet. We happened to arrive in our few loud seconds and found that our few loud seconds do not appear to overlap with anyone else's. Some astronomers, when they talk about this in informal settings, use a phrase that captures the observation without the theory. They call it the Great Quiet, not the Great Filter, which is a specific argument about what mechanism prevents civilizations from persisting or expanding, just the quiet. The observation that the receiver is on has been on for decades, and the signal level is essentially zero. Some of that zero is certainly because the universe is genuinely sparse with intelligent life at this particular moment. Some of it is almost certainly because some of the voices that might have answered have already finished speaking. The library is real, the shelves are full, the lights are off. Whether anyone is currently inside is a question we do not yet have an instrument fine enough to answer. What we have is the shape of the building and a growing sense, year by year, of how many rooms it contains. If you want to know what one of those quiet rooms looks like up close, not as an abstraction, not as a statistical exercise, but as an actual physical place you could theoretically stand in, you do not have to travel far at all. We already have one. It is right next door. Mars is the easiest dead world to begin with. because it is a place you can actually locate on a clear night without any equipment at all. You step outside at the right time of year, you find the small, steady reddish point of light that does not twinkle the way stars do, and there it is. The fourth planet from the sun, the next one out from ours. The neighbor. For most of human history, it was nothing more than a wandering light with a name borrowed from a god of war, a point in the sky that moved against the background of fixed stars in a pattern that took ancient astronomers years to work out. It became something closer to a real place in the late 19th century, when telescopes became powerful enough to show that the reddish dot had features, polar caps, that expanded and contracted with the seasons. Dark regions that some observers convinced themselves must be vegetation, changing color as they spread and receded, a surface with markings that looked, through the instruments of the day, like they might mean something. The Italian astronomer Giovanni Schiaparelli reported in 1877 that he could see long, straight features crossing the Martian surface, which he called canali, a word that in Italian means channels, in the neutral geological sense, but which translated into English became canals, which carries an entirely different implication. An American astronomer named Percival Lowell took that implication and ran with it. Lowell had resources, enthusiasm, and a private observatory in Arizona that he built largely for the purpose of studying Mars. Over the following decades, he published maps and books and lectures arguing that the straight lines he saw were an enormous engineering project, an irrigation network constructed by a dying civilization moving the last of their planet's water from the polar ice caps to the warmer equatorial regions where it could still sustain life. The civilization was in decline, he wrote. The planet was drying out. The canals were the desperate response of an intelligent species trying to survive on a world that was slowly losing everything it needed to keep them alive. None of it turned out to be true. The canals were an artifact of the human visual system under strain the eye trying to resolve faint, scattered markings in a blurry telescopic image tends to connect them into lines that are not actually there. The dark regions were dust and exposed stone, not vegetation. There were no canals. There was no dying civilization. When the first spacecraft actually reached Mars in the 1960s and began returning photographs, what they showed was a cratered, desiccated, airless-looking world that bore no resemblance to Lowell's romantic vision. The early images were so desolate that some scientists worried the results would set back public interest in planetary exploration for a generation. And yet, as it turned out, Lowell's basic intuition that Mars was a dying world, that it had once been different, that something had been lost was not entirely wrong. He had the mechanism wrong and the inhabitants wrong and nearly every specific detail wrong, but the broad shape of the idea that Mars had, once had, conditions it no longer has, that something had changed, that the planet we were looking at was not the planet that had always been there. That part was closer to the truth than anyone realized at the time. The Mars we observe today is, by any reasonable definition, dead. The average surface temperature is approximately -63 degrees Celsius. That is roughly the coldest temperature ever recorded anywhere in Antarctica. And in Antarctica, that temperature is an extreme outlier measured at the most hostile research stations on the planet. On Mars, that is the average, not the cold snap, the average. The atmosphere is so thin, less than 1% of Earth's surface pressure, that liquid water placed on the Martian surface would simultaneously begin to boil from the low pressure and freeze from the low temperature, skipping the liquid phase almost entirely and passing directly between solid and gas. The sky is not blue. There is not enough air to scatter sunlight the way Earth's thick atmosphere does. The sky is a pale, washed-out butterscotch color during the day, fading to shades of pink and brown at sunset. The sun, when you find it, is noticeably smaller and dimmer than it appears from Earth, a smaller pale disk in a larger pale sky. The horizon is closer than it would be on Earth, because Mars is a smaller world and the curvature of the surface falls away faster. It is a place where the cold reaches up through the soles of your boots within minutes, and the silence is absolute in a way that no place on Earth is ever quite silent because there is not enough air for sound to carry any meaningful distance. It feels, If you let yourself sit with the images the rovers have sent back over the decades, like a place where something used to happen, that feeling, it turns out, is correct. Here is what the geology tells us. Mars once had a magnetic field, a real one, a global one generated by a liquid metal core spinning at the center of the planet in the same way that Earth's core spins now, driving the dynamo that produces our own magnetosphere. That field did exactly what Earth's field does for us. It deflected the solar wind, the constant outflow of charged particles that the sun throws in every direction at roughly 400 kilometers per second. The field was a shield. With the shield in place, whatever atmosphere Mars had could be retained. With the shield in place, water on the surface could remain water. With the shield in place, there was a sky substantial enough to press down on the surface with real weight, to scatter light, to hold heat, to make weather. Then the shield went down. The evidence for this comes from multiple directions: paleomagnetic analysis of Martian meteorites that have fallen to Earth, measurements of residual magnetic signatures preserved in ancient crustal rocks, and data gathered by orbiting spacecraft. The current best estimate is that Mars's global magnetic field collapsed somewhere around 3.9 billion years ago. Some recent studies, including work published out of Harvard in 2023 and refined through follow-up analyses in the years since, suggest the field may have persisted slightly longer in some regions than earlier models indicated. But the headline does not change. The core cooled. The dynamo stopped. The shield went away. What happened after that was not an event. It was a budget. A slow, relentless, one-directional loss. The solar wind, no longer deflected, began stripping the top of Mars's atmosphere away, not in a catastrophe, not in a single dramatic episode, but molecule by molecule, particle by particle, over hundreds of millions of years. The lighter gases went first. The heavier ones lasted longer but eventually followed. The atmospheric pressure at the surface began dropping. As it dropped, the ability of liquid water to exist on the surface declined. As the water left, the chemistry that had been cycling carbon dioxide through rocks and atmosphere and oceans the way Earth's carbon cycle does, had fewer and fewer pathways to operate through. The planet began to dry. The sky began to thin. The temperature at the surface began to swing more wildly as the insulating blanket of air grew too sparse to buffer the difference between day and night. Today, Mars has a surface pressure somewhere between 6 and 14 millibars depending on altitude and season. Earth's surface pressure is 1,013 millibars. Mars, in other words, has less than 1% of the atmospheric pressure we have here. To find air that's sparse on Earth, you would need to ascend to an altitude of roughly 30 kilometers, approximately 3 times the cruising altitude of a commercial passenger jet. That is the kind of air Mars has at ground level. But before all of that happened, there was a window, a long window, and inside that window, something was different. The Curiosity rover landed in Gale Crater in August of 2012 and has spent more than a decade driving slowly up the slopes of a central mountain that rises from the crater floor, examining the rock layers the way you might read pages of a very old book. What those layers have told us is that Gale Crater was once a lake. The evidence for this is not ambiguous. It is written in the rock in multiple overlapping languages simultaneously. The mudstones have the fine grain that only forms when sediment settles slowly through standing water. The pebbles embedded in some layers are rounded and smooth in the way that pebbles become when water tumbles them over long distances. The mineral composition includes clay minerals that form specifically in the presence of liquid water and salt deposits that precipitate when standing water evaporates slowly over time. Everything in the rock record of Gale Crater is consistent with a deep freshwater lake fed by rivers draining from the surrounding highlands, persisting in that location on and off for a very long time. The current estimate, based on the mineral evidence Curiosity has gathered, is that the lake existed in some form for approximately 700 million years, with clearly habitable conditions. Conditions where liquid water was present and the chemistry was compatible with the kind of biology we know from Earth, persisting until somewhere around 3.1 billion years ago. 700 million years. That number is worth slowing down for. Complex animal life on Earth. Not microbes, not single-celled organisms, but but animals with bodies and limbs and sensory organs has only existed for approximately 600 million years. The Cambrian explosion, the event in Earth's fossil record where animals with hard parts first appeared in significant numbers, happened about 540 million years ago. Mars had a habitable lake environment that lasted longer than the entire history of complex animal life on this planet. And during the same era, life on Earth was not waiting patiently for conditions to improve. The earliest convincing evidence of microbial life preserved in Earth's rock record dates to approximately 3.5 billion years ago. Some hints, contested but real, push that date back to 3.8 or 3.9 billion years, which means that both planets Earth and Mars were running what amounts to the same experiment at the same time. Both had liquid water, both had atmospheres, both had the chemical ingredients, both had energy sources in the form of volcanic heat and hydrothermal systems. On one of them, life demonstrably took hold and is still here. On the other, the conditions ran for 700 million years, and then the experiment ended, and we still do not know whether anything used them, which is what makes Jezero Crater so important, and what makes what Perseverance found there so difficult to look away from. The Perseverance rover arrived at Jezero Crater in February of 2021. Like Gale, Jezero was once a lake. Unlike Gale, Jezero has something that Gale does not: a clearly preserved ancient river delta, visible from orbit as a fan-shaped deposit of layered sediment, spreading out across the crater floor, exactly where a river once entered from the surrounding highlands and slowed as it met standing water. Deltas are geologically important for the same reason they matter in biology. They are places where sediment carried by moving water is deposited in slow, fine layers, layer after layer, preserving whatever was in the water at the time. On Earth, river deltas are among the most productive biological environments anywhere. They are where nutrients concentrate. They are where organic material accumulates. They are where, if life existed in the water upstream, the chemical evidence of that life tends to be preserved most reliably in the rock record. Perseverance was sent to Jezero specifically because of that delta. It has been sampling rocks across the delta since its arrival. In July of 2024, the rover drilled into a rock the team designated Chayava Falls and extracted a small cylindrical core now sealed inside a metal sample tube. The team noticed something immediately. The rock contained small nodules, dark-colored, chemically distinct from the surrounding matrix, distributed through the sediment in patterns that were not random. Some of the nodules resembled, in the team's description, poppy seeds. Others formed clusters and irregular patches, the team described as leopard spots. Chemical analysis performed by instruments aboard the rover identified the nodules as concentrations of a mineral called vivianite, an iron phosphate, alongside another mineral called greigite, which is an iron sulfide. Both minerals are real. Both were detected with multiple instruments cross-checking each other's results. On Earth, that combination means something specific. Vivianite and greigite appearing together with organic carbon in fine-grained sedimentary rock in those kinds of spatial patterns is what certain iron-reducing bacteria produce as a byproduct of their metabolism. These are microbes that live in low-oxygen environments and extract energy by transferring electrons between iron and sulfur compounds, a form of chemical respiration that does not require oxygen, and that was, in the early history of Earth, one of the dominant modes of microbial life. The mineral combinations and spatial arrangements Perseverance documented are, on Earth, a textbook entry under microbial biosignature. The paper describing the find was published in the journal Nature in September of 2025, following a year of careful internal review and external scrutiny. The authors are precise with their language, in the way scientists are precise when they understand they are writing about something that might matter enormously. The phrase they use is potential biosignature. They list every alternative explanation they can construct: certain volcanic processes, specific water-rock interactions that they claim that what they found is the kind of thing that, on Earth, would be the first thing a geobiologist pointed to, and that the non-biological explanations, while they exist, require specific conditions that have not been independently confirmed in the rock. The sample is sitting on the surface of Mars right now, in its sealed tube, in the wind. The Mars Sample Return Mission, which was designed to retrieve the tubes Perseverance has been collecting and bring them back to Earth for analysis by laboratories equipped to do things no rover instrument can do, is currently under review. The original architecture has been reconsidered. The budget is being restructured. The timeline, already stretched from earlier optimistic projections, has been pushed further. The current working estimate for when a sample return mission might bring that tube home is somewhere in the late 2030s, possibly later, which means that the most scientifically consequential rock sample our species has ever identified is going to remain on another planet for at least another decade, waiting for us to develop the political will and the funding and the engineering to go and collect it. There is a particular kind of photograph that exists in old houses. You find them sometimes in boxes, in attics, or in drawers, in rooms that have not been regularly used. They are photographs of people you have never met, in places you have never been, wearing clothes from a time before your own. The people in the photographs are real. They lived in real places and had real lives and walked through rooms that in some cases still exist. But they are gone, and the photograph is all that is left of the moment it captured. You are holding a piece of time that has been separated from the people it came from. That is what Shayava Falls is, a piece of time, a moment from 3 billion years ago, sealed in rock, waiting to be read. Maybe inside that moment there is evidence of something that was alive. Maybe the chemistry assembled itself into those patterns without any biology involved at all, the way certain geological processes can produce structures that superficially resemble the products of life. We do not know. The image is real. What it shows is still being worked out. If you have ever moved into a house that someone else lived in before you and made the mistake of going up into the attic, you know the specific quality of the feeling that comes with finding a box of photographs of strangers. Real people, real faces, real lives conducted in the same physical space you now occupy. You are holding evidence of an existence you can almost reach across and touch, and you cannot. The distance is not spatial, it is temporal. The house is the same house. The people are unreachable. Mars is that attic. The box is real. The photographs may be real. The camera stopped working a very long time ago. The dead world that gets the least attention is not Mars. Mars has the rovers. Mars has the sample tubes. Mars has the magazine covers and the long-term colony proposals and the decades of accumulated cultural imagination projecting human futures onto its red surface. Mars is the one we talk about. The one we mostly do not talk about is the planet on the other side of us, the one that sits between Earth and the Sun, closer to us than Mars ever gets, visible on clear evenings as the brightest object in the sky after the Moon itself. That planet is Venus. And the reason we do not talk about it the way we talk about Mars is not because it is less interesting. It is because what happened there is harder to look at directly. In school, Venus gets approximately 1 week of attention. You learn that it is the hottest planet in the solar system, despite not being the closest to the Sun. You learn that this is because of the greenhouse effect carbon dioxide in the atmosphere, trapping heat the way a blanket traps warmth. You learn that it is an example of what can go wrong when a planet's atmosphere gets out of balance. The teacher draws the diagram, makes the point about carbon dioxide, and moves on. The lesson is a cautionary tale about atmospheric chemistry, and then it is over. That telling is incomplete in a way that matters. What it leaves out is the part that changes how you think about Venus entirely. Venus, on paper, is Earth, not approximately Earth, not Earth in a loose poetic sense. Venus is Earth in the specific technical sense that planetary scientists mean when they compare worlds. It has a diameter of approximately 12,100 kilometers. Earth's diameter is approximately 12,700 kilometers. The difference is less than 5%. Venus has a mass of approximately 82% of Earth's mass. Its density is nearly identical to ours. It formed at roughly the same time as Earth, out of the same rotating disk of gas and dust that gave birth to the entire inner solar system, from the same general chemical inventory of silicates and iron and volatile compounds. It sits in the inner solar system close enough to the Sun to receive substantial energy, far enough to have once been within the range where liquid water was not immediately ruled out. By every parameter that astronomers used to use when they talked about planets being sisters: size, mass, density, composition, age, formation, history, Venus and Earth are sisters. If you showed a planetary scientist the basic specifications of two anonymous rocky planets and asked them to identify which one was more likely to support life, and the specifications were those of Venus and Earth, they would have no reliable way to tell from the numbers alone. The numbers are too similar. The numbers point in the same direction for both. Now hold that thought, because here is the part I want you to sit with for a moment before we move forward. Venus may have had liquid water oceans on its surface for somewhere between 2 and 3 billion years. That is not speculation offered without support. That is the conclusion of detailed, three-dimensional climate modeling conducted by scientists at NASA's Goddard Institute for Space Studies. The work, originally published in 2016 by Michael Way and Anthony Del Genio, and refined through subsequent studies over the following years, takes what we know about Venus's likely early conditions, its probable early rotation rate, its distance from the young Sun, its likely early atmospheric composition, and runs a full global climate simulation forward through time. Under reasonable assumptions about cloud distribution and rotation, the model produces a Venus with a stable temperate climate, moderate surface temperatures, and liquid water oceans that persist for somewhere between 2 and 3 billion years before the planet transitions into the state it is in now. 2 to 3 billion years of liquid surface oceans on Venus. Let that number find its proper scale. Complex multicellular life on Earth, not microbes, but animals, organisms, with differentiated tissues and coordinated biological systems, has existed for approximately 600 million years. The entire history of animals on this planet fits inside that 600 million year window. Venus, on the climate models, had surface ocean conditions for 3 to 5 times as long as the entire history of animal life on Earth, for longer than any named animal lineage has existed anywhere. For a span of time so large that it contains within itself multiple complete cycles of the kind of biological complexity, build-up and extinction and recovery that has characterized Earth's own history. Whether anything lived in those oceans is a question we cannot currently answer. We have no fossils from Venus. We have no surface samples from Venus in any meaningful sense. The Soviet Venera program, which represents the entirety of humanity's direct surface contact with Venus, managed to land a series of spacecraft on the Venusian surface between 1970 and 1982. The most successful of them, Venera 13, survived on the surface for 1 hour and 57 minutes before the heat and pressure destroyed it. The images it transmitted in that time show a flat landscape of broken angular rock slabs under a heavy yellow-orange sky. No organisms, no structures, no indication of anything biological in any form. But Venera 13 landed on the Venus of today. The question of whether anything existed in the oceans of the Venus of 2 billion years ago is a question that those images cannot answer in either direction. Then something changed. The exact trigger for Venus's transformation is one of the genuinely open questions in planetary science. The leading candidates are not mutually exclusive, and the current evidence suggests more than one of them may have contributed. The first candidate is large-scale volcanic, resurfacing a period, possibly lasting between 50 and 100 million years in geological terms, during which the entire surface of Venus was effectively repaved by volcanic activity on a scale that has no equivalent in Earth's more recent history. The evidence for this comes from the relative uniformity of Venus's surface age. As measured by crater counts, the surface is old, but not differentially old in the way you would expect if different regions had been geologically active at different times over billions of years. It looks instead like a surface that was all reset at roughly the same time. If that resurfacing event released sufficient quantities of volcanic gases, carbon dioxide, sulfur dioxide, water vapor, into the atmosphere over a geologically short period, It could have pushed the climate system past a threshold it could not recover from. The second candidate is the gradual brightening of the sun. The sun, as we will discuss in more detail shortly, has been increasing in luminosity throughout its lifetime. Over the last 4.5 billion years, it has brightened by approximately 30%. The inner edge of the habitable zone, the distance from the sun inside which water worlds tend to lose their oceans, has been moving steadily outward as the sun has brightened. Venus's orbit, already closer to the sun than Earth's, was always more vulnerable to this drift than ours. As the sun brightened, the energy Venus received each day increased. At some point, the increased energy may have been enough to begin destabilizing the climate system even without any additional volcanic contribution. The third candidate is the possibility that both of those things happened in proximity to each other, and that the combined effect crossed a threshold that neither alone might have crossed on the same timeline. Whatever the trigger, the mechanism that followed is what planetary scientists call a runaway greenhouse effect, and the word runaway is earning its place in that phrase. Here is how it works. Water vapor is itself a greenhouse gas. It traps heat in the atmosphere. As the surface of Venus warmed, more water evaporated from the oceans into the atmosphere. The additional water vapor trapped additional heat. The additional heat caused additional evaporation. The additional evaporation put more water vapor into the atmosphere. The cycle fed itself. The warmer the atmosphere became, the more water it could hold. The more water it held, the warmer it became. This is not a self-limiting process. It does not find a new equilibrium at a slightly higher temperature and stabilize. It accelerates. The oceans began evaporating, not slowly, but increasingly quickly as the feedback strengthened. The water vapor in the upper atmosphere was then exposed to solar ultraviolet radiation, which broke the water molecules apart into their constituent hydrogen and oxygen atoms. The hydrogen, being light, drifted upward and was gradually stripped away by the solar wind into space. The oxygen, being heavier, largely bonded with iron and other minerals in the surface rocks and was absorbed into the crust. The water was not just evaporated, it was chemically dismantled and scattered. The hydrogen went one way, the oxygen went another. The molecule that had filled the oceans for billions of years ceased to exist as a molecule. Once the water was gone, the carbon dioxide that had previously been dissolved in the oceans and locked into carbonate rocks through geological cycling was released back into the atmosphere with nothing to reabsorb it. The atmosphere thickened, the surface pressure climbed, the temperature climbed. The process compounded itself until it reached the state it is in today, which is a state that should be described slowly and specifically so that its full character arrives properly. The average surface temperature on Venus today is approximately 462 degrees Celsius. That is 864 degrees Fahrenheit. It is hot enough to melt lead. It is hot enough to melt zinc. It is hot enough that most of the metals we use in everyday engineering would be liquid on the surface of Venus. There is no place on Earth with a surface temperature anywhere near that. The hottest natural temperature ever recorded on Earth's surface is a fraction of that. The surface pressure on Venus is approximately 92 times Earth's atmospheric pressure at sea level. To find a pressure that high on Earth, you would need to descend to a depth of approximately 900 meters below the ocean surface. Not 9 meters, 900. The deepest any human-occupied vessel has descended for exploration is just over 11,000 meters in the Mariana Trench. The pressure at the bottom of the Mariana Trench is about 1,096 times sea level pressure. The pressure on Venus's surface, in other words, is approximately what you would experience at roughly 900 meters depth in the ocean, crushingly high by any terrestrial standard, less than the deepest ocean trench, but far beyond anything a human body could survive without engineering specifically designed for it. The clouds that give Venus its bright reflective appearance from Earth are not water clouds, they are clouds of sulfuric acid. The cloud layers extend from roughly 45 kilometers to about 70 kilometers above the surface. Within those clouds, it rains. The rain is sulfuric acid. The rain does not reach the surface. The lower atmosphere is so hot that the sulfuric acid droplets evaporate back into vapor before they fall far enough to land. The weather on Venus has precipitation that never arrives. The sky rains, and the rain disappears on the way down. If you could somehow stand in the lower atmosphere of Venus, which you could not, for reasons that by now require no explanation, you would be beneath a ceiling of acid clouds in air nearly 100 times denser than Earth's, at a temperature sufficient to melt the metal in your bones, under a sky that is perpetually raining, something that will never touch the ground. This is what Venus is now. The planet that may have had oceans longer than animals have existed on Earth. The planet whose basic specifications are indistinguishable from ours in a table of planetary properties. The planet that is, in every sense that matters to the physicist, our nearest twin. There is an ordinary experience that captures the transition more precisely than any diagram. You put a pot of water on the stove, you turn on the burner, you walk away intending to return when the water boils, but something pulls your attention, a conversation, a message, a moment of distraction that stretches longer than you meant it to. When you come back, the burner is still on, the water is long gone, the bottom of the pot is discolored and beginning to glow at the edges. The pot is still there. The pot is fine in the structural sense, but what was inside it is not there anymore, and the burner has not stopped. Venus has been a glowing pot for approximately 700 million years. The burner is the sun. The burner does not turn off. Now here is the detail that I find most difficult to move past once I have noticed it. The oceans do not vanish cleanly. They leave something behind. Not water, not ice, not any molecule you could collect and analyze and say, here, this is what the ocean became. They leave a ratio. Hydrogen comes in two forms. The common form, which makes up the vast majority of hydrogen everywhere in the universe, has a nucleus consisting of a single proton. The rarer form, called deuterium, has a nucleus with a proton and a neutron. It is heavier. On Earth, deuterium makes up approximately 1 part in 6,400 of the hydrogen in our oceans. It is rare. Now, when a planet's water is being broken apart by ultraviolet radiation in the upper atmosphere, the two forms of hydrogen do not leave at the same rate. The lighter form moves faster at any given temperature. Faster-moving atoms are more likely to reach the escape velocity needed to drift away from the planet's gravity and be carried off by the solar wind. So the light hydrogen leaves preferentially. The deuterium, being heavier and slower on average, is less likely to escape. Over billions of years of this process, the ratio of deuterium to ordinary hydrogen in whatever water remains in the atmosphere gradually rises, because the ordinary hydrogen is leaving faster. When scientists measure the ratio of deuterium to ordinary hydrogen in Venus's atmosphere today, they find a value approximately 150 times higher than the ratio in Earth's oceans. 150 times. That is not a subtle signal. That is not an ambiguous measurement. That is a number with one coherent explanation. And the explanation is that Venus once had vastly more water than it has now, that this water was broken apart and its components driven into space over billions of years, and that the heavier hydrogen was left behind in disproportionate amounts as the lighter hydrogen escaped preferentially. The number in Venus's atmosphere today is the chemical fingerprint of an ocean that no longer exists. The ocean is gone. The memory of the ocean, encoded in an isotope ratio, is still there in the air. It is measurable. It is real. It is, in a precise technical sense, the ghost of a body of water that may have covered much of a planet's surface for 2 to 3 billion years. There is a kind of grief that comes with that detail if you let it arrive fully. We do not usually allow planets to have ghosts. Ghosts belong to the vocabulary of human loss, but Venus has one, and it is not metaphorical. It is chemical. It is quantifiable. You can point to the number on the spectrometer and say, here, this is where the ocean went. This is the shape of the absence. This is what 2 billion years of water leaves behind when the water is taken apart and scattered, and the heavier pieces settle into the air because they had nowhere else to go. And here is the part that extends beyond Venus itself. The James Webb Space Telescope, which has been operating since 2022 and is now producing atmospheric measurements of exoplanets at a level of detail that was not possible before its launch, is capable in principle of detecting isotope ratios in planetary atmospheres at distances of tens of light years. The generation of ground-based, extremely large telescopes currently under construction, including the Extremely Large Telescope in Chile, expected to see first light in the late 2020s, will push that capability further. The first time we measure a deuterium-enriched atmosphere on a rocky exoplanet and recognize it for what it is, we will not be making a new discovery. We will be reading an obituary that the planet wrote for itself over billions of years. We will be standing far away, unable to go there, reading the chemical record of an ocean that dried up long before any telescope capable of detecting it existed. We will know that world used to have water. We will know the water is gone. We will not know whether anything lived in it while it was there. Venus's porch light is still on. It has been on for 4 billion years. The light comes from the sun shining on the cloud tops. The house burned down inside. The cloud tops are bright. The surface beneath them is a place where the concept of habitability does not apply in any form. 2 worlds in our immediate neighborhood. One died cold and slow as its magnetic shield failed and its atmosphere bled away over hundreds of millions of years. One died hot and fast, in a feedback cascade that dismantled its own oceans. Different mechanisms, different timescales, same destination. And Earth, sitting between them, still warm, still wet, still breathing, not because it is a fundamentally different kind of world, but because its particular combination of circumstances has so far kept the window open. That combination is not permanent. It is not even unusual that it should eventually end. What is unusual is that it has lasted this long. What is unusual is that we are inside it right now, tonight, able to look outward at both directions of the same story and recognize where we are in it. That recognition is the whole thing. That recognition is what changes how the sky looks. And the sky is about to look different in one more way, because the neighborhood is not the limit of the lesson. The habitable zone itself, the concept we use to organize our search for life-bearing worlds, has a problem built into it that we usually do not acknowledge when we talk about it. And once you see the problem, you cannot look at the catalogue of 6,000 worlds the same way again. When most people first encounter the concept of the habitable zone, the image that settles into their thinking is something like a ring drawn around a star on a diagram. Inside the ring, conditions are right. Outside the ring, they are not. Planets that fall inside the ring are the interesting ones, the candidates, the worlds worth paying attention to. Planets outside the ring are ruled out. Earth falls inside the ring, which is why we are here. The ring is where the good planets live. That image is clean, and it is memorable, and it is, in the ways that matter most, wrong. The habitable zone is real. The mathematics behind it are real and carefully derived. It is defined, in the most commonly used formulation, as the range of orbital distances from a star at which a planet with a rocky surface and a reasonable atmosphere could maintain liquid water on that surface under equilibrium conditions. For our Sun, at its current luminosity, the habitable zone spans roughly from 95% of Earth's orbital distance from the Sun out to approximately 170% of it, depending on which research group's model you are using and what assumptions they have made about clouds and atmospheric composition. The inner boundary is set by the point at which water vapor feedback becomes self-sustaining, and the planet tips into a runaway greenhouse. The outer boundary is set by the point at which carbon dioxide begins to condense out of the atmosphere as dry ice. Those boundaries are real. The zone between them is real. But the zone moves. It moves because stars are not the static, unchanging objects. They appear to be from the perspective of a human lifetime, or even a human civilization. They look unchanging to us because we are brief and stars are slow. Over billions of years, every star on what astronomers call the main sequence, the long stable phase of a star's life, during which it fuses hydrogen into helium, in its core gradually increases in luminosity. The mechanism is straightforward. As hydrogen in the core fuses into helium, the helium accumulates. Helium is denser than hydrogen. The core becomes slightly more compact. The increased density raises the pressure. The raised pressure raises the temperature. The raised temperature increases the rate of fusion. The increased fusion rate produces more energy. The star gets brighter. The rate of brightening for a star like our Sun is approximately 10% per billion years. That sounds modest. In the context of a single human life, or a single civilization, or even a single species, it is invisible. Over geological time, it is not modest at all. Over the 4.5 billion years since the solar system formed, the Sun has brightened by approximately 30%. 30% more energy arriving at Earth's surface now than when the planet was new. 30% more energy than the young Earth received from its young star. That number creates a problem that planetary scientists call the faint young sun paradox, and it is worth understanding because it reveals something important about how delicately Earth's climate system has been calibrated throughout its history. The paradox is this: if you take the Sun as it is today and reduce its output by 30% to simulate the young Sun, the models say the early Earth should have been frozen solid. The amount of solar energy reaching the planet would have been insufficient to keep liquid water at the surface. Yet the geological record shows clear evidence of liquid water on Earth's surface, going back at least 4 billion years, possibly 4.4 billion. Liquid water was present on Earth when the Sun was significantly fainter than it is now. The planet was warm enough when, by simple solar energy calculations, it should have been a frozen ball. The resolution most planetary scientists favor involves a much denser early atmosphere, with substantially higher concentrations of greenhouse gases, carbon dioxide, methane, perhaps others providing enough insulation to compensate for the weaker sunlight. As the Sun gradually brightened over billions of years, the atmospheric greenhouse was gradually reduced through geological processes that removed carbon dioxide from the air, keeping the surface temperature within a range that liquid water could persist in. The thermostat of the early Earth was set much higher than it is today, and it has been slowly turned down as the heat source has turned up. The two trends have roughly tracked each other, keeping the surface temperature within the range that liquid water requires. The balance has held. So far, the balance will not hold indefinitely. As the Sun continues to brighten at its 10% per billion year rate, the inner boundary of the habitable zone continues to move outward. The orbital distance at which the runaway greenhouse threshold is reached creeps steadily away from the Sun. Today, that inner boundary sits inside Earth's orbit, meaning Earth is currently safe from that particular cliff edge. But the margin is not enormous, and it is shrinking. The most careful modeling of Earth's long-term climate future, incorporating the brightening Sun and the feedbacks of the carbon cycle and the water vapor cycle, converges on a window of approximately 1 to 1.5 billion years from now, before conditions on Earth's surface become untenable for complex multicellular life. The mechanism is the same one that destroyed Venus, only slower. As the Sun brightens, the surface warms. The warmer surface drives more water vapor into the upper atmosphere. The upper atmosphere water vapor is broken apart by ultraviolet radiation. The hydrogen escapes to space. The oceans gradually lose water. The chemistry of the surface changes. The kind of world that supports forests and animals and rain and seasons runs out of the conditions it requires. 1 to 1.5 billion years. That sounds like an enormous amount of time, and measured against a human life, it is incomprehensible. Measured against the planet's own history, it is not. Earth has been habitable for approximately 4 billion years. It has roughly 1 to 1.5 billion years of habitability remaining for complex life. The largest portion of this planet's life-bearing history is already behind us. We are not in the morning of Earth's habitable era. We are in the afternoon, with the evening visible on the horizon. The way I find myself thinking about this uses an image that most people have encountered in some form. You are learning to play a musical instrument, and you are working on a piece that requires your left hand to cover a specific range of notes, an octave, 8 adjacent keys within reach of your fingers when your hand rests in one position on the keyboard. Within that octave, you can play anything the piece requires. The notes work, the music is possible, but the keyboard is not stationary. Someone is very slowly sliding it across the table while you play. The keys you can reach shift gradually. The notes that were in your range drift out of it. New notes drift in from the other side. The playable range is always exactly 1 octave wide, but which octave it corresponds to on the keyboard changes over time. The habitable zone is that octave. The brightening star is the hand sliding the keyboard. Mars was in the playable range once. Its keys drifted out of reach approximately 3.5 billion years ago, assisted by the collapse of its magnetic field. Venus was in the playable range once. Its keys slid out of reach approximately 700 million years ago. Earth's keys are currently in the middle of the playable range. The keyboard is still moving, the keys are still drifting. Now, we have to talk about most of the catalogue, because most of the 6,000 confirmed exoplanets and most of the hundreds of billions of estimated planets in this galaxy do not orbit stars like the Sun. The Sun is a specific kind of star, what astronomers classify as a G-type main sequence star, sometimes called a yellow dwarf, with a surface temperature of approximately 5,800 Kelvin, a mass of one solar mass by definition, and an expected main sequence lifetime of approximately 10 billion years. Our Sun is currently about halfway through that lifetime. G-type stars make up roughly 7% of the stars in the Milky Way. They are not rare, but they are far from dominant. The dominant type of star in the galaxy, accounting for approximately 75% of all stars, is something called an M-type main sequence star, or red dwarf. Red dwarfs are small, ranging from about half the Sun's mass down to about 8% of it at the lower limit of what can sustain nuclear fusion. They are cool, with surface temperatures between roughly 2,400 and 3,700 Kelvin compared to the Sun's 5,800. Because they are cool, they emit most of their light in the infrared, with the visible portion of their spectrum weighted toward red. They are dim. A red dwarf at the lower end of the mass range puts out so little visible light that if you replace the Sun with one, the Earth would be in a permanent dim twilight indistinguishable from late evening at any hour of the day. They are also, by a substantial margin, the longest-lived stars in the universe. The smallest red dwarfs are expected to remain on the main sequence for trillions of years, numbers so large they have no intuitive meaning, because the universe itself is only 13.8 billion years old. No red dwarf that has ever formed in the history of the universe has yet died of old age. Every red dwarf that has ever existed is still burning. That means that when we look at M-type stars, we are looking at objects whose habitable windows, if they have them, stretch across timescales that make the entire current age of the universe look like an opening act. On the surface, that sounds like good news for life. Long-lived stable stars with habitable zones that planets can sit in for trillions of years. The problem is that red dwarfs are not gentle. They are, particularly when young, magnetically violent in ways that our Sun is not and has never been. Magnetic activity in stars is related to their convective structure, the way energy moves from the interior to the surface. Red dwarfs, especially the smaller ones, are fully convective throughout their entire volume, meaning the hot plasma from the core circulates all the way to the surface and back. This full convective mixing drives intense, tangled magnetic fields that erupt through the surface in the form of star spots and flares. A stellar flare is a sudden, enormous release of electromagnetic energy, ultraviolet radiation, X-rays, and in the most powerful events, energetic particles traveling at significant fractions of the speed of light. Our Sun produces flares. The most powerful solar flare ever directly measured, the Halloween storms of 2003, temporarily disrupted satellite communications and produced radiation levels that were hazardous to astronauts in orbit. It was, by solar standards, an exceptional event. A comparable event on an active red dwarf would not be exceptional. It would be routine. Red dwarf flares can exceed the energy output of the most powerful solar flares by factors of 10,000 or more, and they happen not rarely but constantly. The TRAPPIST, one system, which sits approximately 40 light-years from Earth and contains 7 rocky planets in orbits around a red dwarf star, is one of the most closely studied planetary systems outside our own. 3 of its 7 planets orbit within the conventional habitable zone of their host star. On paper, it is exactly the kind of system that exoplanet scientists dream about: multiple Earth-sized rocky worlds around a nearby star, several of them at distances where liquid water could in principle exist. Sustained observations of TRAPPIST, one conducted with the James Webb Space Telescope in 2025, measured the flare activity of the host star over an extended period and found that the star produces approximately 6 flares per day. 6 per day, every day. More than 2,000 per year, every year, for billions of years into the past and trillions of years into the future. The planets sitting in the habitable zone of TRAPPIST, one orbit closer to their star than Mercury orbits the Sun, they are not receiving these flares from a comfortable distance. They are receiving them at close range, with no buffer of distance to attenuate the radiation before it arrives. Laboratory studies attempting to simulate the radiation environment on TRAPPIST, one habitable zone planets, have exposed cultures of Earth's most radiation-tolerant organisms, including Deinococcus radiodurans, a bacterium capable of surviving radiation doses that would kill any other known organism almost instantly, to estimated TRAPPIST-1 flare conditions. The results vary by study and by the specific assumptions made about planetary atmosphere and magnetic shielding. The general picture is that flares of this intensity, arriving with this frequency, are sufficient to sterilize any unprotected surface and any shallow water environment. Life might persist deep underground. Life might survive in subsurface oceans beneath thick layers of ice or rock, but the open surface environments, the running water, and exposed soil and sunlit seas that complex life on Earth depends on, are very difficult to maintain on a world being irradiated at that level every few hours for its entire existence. There is another structural problem with habitable zone planets around red dwarfs, and it is built into the geometry of the situation. Because the habitable zone around a red dwarf is so close to the star, the gravitational interaction between the star and any planet orbiting at that distance is strong enough to do something to the planet's rotation over geologically short timescales. It locks it. The technical term is tidal locking, and it means exactly what it sounds like. The same gravitational interaction that keeps our moon showing the same face to Earth at all times. The moon rotates once on its axis for every orbit it completes around Earth, so the same hemisphere always faces us, operates between a red dwarf and its habitable zone planets. The planet rotates once per orbit. One hemisphere faces the star permanently, the other hemisphere faces away permanently. One side is in eternal day, receiving constant radiation from a star that never moves in the sky. The other side is in eternal night, cold enough in many models for the atmospheric gases themselves to condense and precipitate out as snow or frost. The boundary between the two hemispheres, the line of perpetual terminator, the ring of permanent dusk, is the only zone where temperatures might be anywhere near moderate. A narrow strip of twilight running around the entire circumference of the planet, where the geometry of sunlight and shadow produces something close to habitability. Climate models disagree significantly about how livable even that strip might be. Some models show that a sufficiently thick atmosphere with the right circulation patterns could redistribute heat from the permanently lit day side to the permanently dark night side, spreading the energy around enough to make broader swaths of the planet potentially usable. Other models show that under slightly different conditions, the atmosphere itself migrates to the night side and freezes out, leaving the day side exposed and the night side buried under a growing deposit of frozen air. Which scenario plays out depends on details we do not yet have for specific planets. The honest answer is that we do not know, and the range of possible outcomes for tidally locked habitable zone planets includes both something like marginal habitability on the terminator strip and something like a planet split between an overheated desert hemisphere and a hemisphere where the air has turned to ice on the ground. So, when the catalogue of confirmed exoplanets reaches 6,000, and the estimated total for the galaxy reaches hundreds of billions, and the subset of those in habitable zones reaches tens of billions, we have to be precise about what those numbers mean. 3 out of every 4 of those planets orbit red dwarfs. 3 out of every 4 of them are sitting closer to their star than Mercury is to the Sun. 3 out of every 4 of them are receiving flares of extraordinary intensity multiple times per day for the entire life of their star. Many of them are tidally locked. The phrase habitable zone applied to these worlds is a description of orbital geometry, not a description of conditions. The geometry is right. Almost everything else is uncertain to the point of requiring substantial qualification before the word habitable does any real work in the sentence. The image I keep returning to is this: A habitable zone planet around a red dwarf is something like trying to maintain a garden directly beneath a faulty electrical transformer that sparks and surges several times a day, every day, without interruption, for billions of years. The soil might be good, the rainfall, if there is any, might be adequate, but every few hours something overhead discharges an enormous pulse of energy across everything in the garden without warning or pattern. Some things might survive that. The hardiest, simplest, most deeply buried things might find ways to persist. But the kind of garden that produces complex growth visible from a distance, with layered ecosystems and interdependent species, and things that require stable conditions to develop over long timescales, that garden is very hard to maintain under a transformer that never stops sparking. That is most of the catalogue. 3 out of every 4 entries. The ones we talk about most often when we talk about potentially habitable worlds. The ones whose numbers make the search for life seem statistically promising. The ones that, when you look at the actual conditions rather than the orbital geometry, are sitting inside a fight that does not end. There are exceptions. Red dwarfs that have aged past their most magnetically active phase and settled into relative quiet. Habitable zone planets around K-type stars, slightly smaller and cooler than the Sun, but substantially calmer than red dwarfs, which represent a middle category that some researchers consider the most promising host stars for complex life. Habitable zone planets around G-type stars like our Sun, which are less common in the catalogue only because they are harder to detect, not because they are rare in the galaxy. Those exist. They are real candidates. They are not, however, where most of the current observations are pointing, because the physics of detection favors the systems that are easiest to see and measure, and those tend to be the compact, close-in, flare-active ones. The porch light at TRAPPIST-1 is on. It flickers 6 times a day. The wiring is unstable. Every few hours the surge comes and the light blazes so intensely that for a moment everything near it is visible in painful detail, and then the baseline resumes, and the steady dim red glow of the star returns, and the planets continue their rapid orbits around it, taking each flare full in the face as they always have and always will, for billions of years before we were here to look. For trillions of years after we are gone, that is most of the lottery. That is the texture of most of the candidates. 3 out of every 4 of the worlds we point to when we want to feel the universe is populated. And the question of whether any of those worlds has anything on it has to be asked against that backdrop. Not against the backdrop of our Sun on a calm afternoon with the ocean visible from a comfortable beach and the air warm and full of the sound of living things going about their ordinary business. Which brings us to a harder question. We have been talking about other worlds, other histories, other timelines. We have been treating Earth as the reference point, the successful case, the one that worked. But Earth's own history, when you actually look at it, is not the story of a world that worked smoothly from the beginning. It is the story of a world that almost stopped working several times, and once almost stopped because of what life itself learned to do. That is where we have to go next. The standard account of Earth is an account of success. The Sun is well behaved. The orbit is stable. The Moon, which formed when a Mars-sized body struck the early Earth and threw an enormous quantity of material into orbit that eventually coalesced into our large natural satellite, stabilized the planet's axial tilt and moderated the seasons. The magnetic field held, the atmosphere held, the water held, life appeared, life diversified. Life filled every available environment from the deepest ocean trenches to the upper atmosphere, from boiling hydrothermal vents to ice sheets kilometers thick. And here we are, the inheritors of 4 billion years of unbroken biological continuity, telling ourselves the story of a planet that worked. That story is true in its broad outline. Earth is, by every measure we can apply to it, an unusually stable and durable world. 4 billion years of continuous habitability is not something we have evidence of anywhere else. It is genuinely remarkable. But the broad outline conceals a texture that changes the meaning of the story considerably. Within those 4 billion years of broad continuity, the lights came very close to going out on multiple occasions. The thread of life on Earth is not a thick rope stretching unbroken from the first cell to the present. It is a series of thinner strands, some of which snapped, some of which held, with the ones that held carrying everything forward each time something catastrophic tried to end it. The fossil record is the primary document of this. It is an incomplete document. Most organisms that have ever lived left no fossil trace at all, and the record we have is heavily biased toward organisms with hard parts living in environments where sediment accumulates, but it is the best record we have of what lived and when. And what the fossil record shows, when you read it carefully, is a history punctuated by events where the diversity of life dropped with a suddenness that the normal background rate of extinction cannot account for. These are the mass extinctions. The major ones have been identified, studied, argued over, and in most cases traced to their causes with reasonable confidence. There are 5 of them that every paleontologist would list if you asked. The Ordovician-Silurian extinction, approximately 444 million years ago, took out roughly 85% of marine species. The cause is debated, but the leading hypothesis involves a period of intense glaciation that cooled the oceans, lowered sea levels, and disrupted the shallow marine environments where most complex life at the time was concentrated. The late Devonian extinction, approximately 372 million years ago, eliminated something like 75% of species over a prolonged interval that may have lasted several million years rather than a single event. The causes here are genuinely uncertain and probably multiple ocean anoxia, climate change, possibly bolide impacts. The Triassic-Jurassic extinction, approximately 201 million years ago, cleared the way for the dinosaurs by eliminating the large reptiles that had previously dominated terrestrial ecosystems. The Cretaceous-Paleogene extinction, 66 million years ago, is the one most people have heard of. The asteroid, the dinosaurs, the sudden end of one world, and the gradual beginning of another. But none of those is the worst one. The worst one by the numbers is the one in the middle of the list. The Permian-Triassic extinction, approximately 252 million years ago, is called by paleontologists the Great Dying, and when you see the numbers, the name does not feel like an exaggeration. Approximately 96% of marine species disappeared in the fossil record at that boundary. Approximately 70% of terrestrial vertebrate species, insects, which are, by any reasonable measure, among the most biologically robust organisms on the planet, they have survived. Every other extinction event in the record had the only mass extinction in their documented history during the mass extinction event in the record. Permian-Triassic event. The fossil record on either side of the boundary layer looks, to a paleontologist reading it for the first time, like 2 different planets. The diversity before is rich, complex, recognizable as Earth. The diversity immediately after is sparse, to the point of strangeness. Almost nothing made it across. The trigger, by the best current scientific understanding, was volcanic. Not a single eruption. A sustained, geologically prolonged series of eruptions in the region of what is now Siberia, a volcanic province called the Siberian Traps, that released extraordinary quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere and oceans over a period estimated at somewhere between 1 and 2 million years. The carbon dioxide drove rapid warming. Estimates of the temperature increase during the event range from 8 to 10 degrees Celsius over a geologically short interval. The sulfur compounds acidified the oceans. The combination of warming, acidification, and reduced oxygen dissolved in the water created conditions in the marine environment that most organisms simply could not tolerate. On land, the rapid temperature increase and the disruption of precipitation patterns eliminated ecosystems that had been stable for tens of millions of years. The recovery from the Permian-Triassic extinction took between 5 and 10 million years before ecological complexity returned to anything resembling pre-extinction levels. 5 to 10 million years. To put that in terms of familiar timescales, the entire existence of our genus, Homo, from the earliest Homo habilis to the present, spans roughly 3 million years. The recovery time from the Great Dying was longer than the entire history of the human lineage. For 5 to 10 million years, life on Earth was in a condition that could reasonably be described as critical. Not gone, not extinguished, but reduced to a fraction of its former complexity, struggling to rebuild in an environment that was still recovering from what had destabilized it. That is the worst extinction event with a clear fossil record. But it is not the worst extinction event in Earth's history. The worst one happened so long ago that the conventional fossil record barely touches it. It happened to organisms so small and so fragile that they left no bodies behind, only chemical signatures and altered rock. And it was caused not by an asteroid, not by a volcano, not by any external force arriving from outside the biosphere. It was caused by life itself, by something life learned to do that it had never done before, by the moment when a particular group of microscopic organisms solved a chemical problem so elegantly and so successfully that their solution poisoned nearly everything else alive on the planet. To understand this, you need to understand what Earth's atmosphere looked like before life changed it. For approximately the first 2 billion years of life's existence on this planet, there was no free oxygen in the air. The early atmosphere was composed primarily of nitrogen, carbon dioxide, methane, water vapor, and trace amounts of other gases. Oxygen was not present as a free gas in any significant quantity because oxygen is chemically reactive, it bonds readily with other elements, and because there was nothing producing it faster than geological processes were consuming it. The organisms living in this early world had evolved in an oxygen-free environment and had built their metabolisms accordingly. They extracted energy from chemical reactions involving hydrogen, sulfur compounds, iron compounds, methane, a variety of processes that we would find profoundly alien today, but that were, in the context of the early Earth's chemistry, perfectly workable. These were the organisms that built the biosphere for its first 2 billion years. Bacteria and archaea, single-celled, microscopic, invisible to any instrument that did not exist yet, running their quiet chemistry in the oceans and on the margins of continents and in the sediments of shallow seas. Then a particular lineage of bacteria evolved something new. The organisms we now call cyanobacteria, the ancestors of the chloroplasts inside every plant cell on Earth today, developed the ability to perform oxygenic photosynthesis. That phrase contains the entire catastrophe in compressed form, so let it expand. Photosynthesis, in general, is the process of using light energy to drive chemical reactions that build organic molecules from simpler precursors. Various forms of photosynthesis had existed before cyanobacteria. What made the cyanobacterial version different was the electron donor. Earlier photosynthetic organisms used hydrogen sulfide, or hydrogen gas, as the source of electrons for their chemistry. Cyanobacteria learned to use water. Water is not rare. Water was everywhere. By switching to water as their electron source, cyanobacteria gave themselves access to a virtually unlimited fuel supply. The chemistry of splitting water to extract electrons releases a byproduct. That byproduct is molecular oxygen, free O2 gas, released directly into the surrounding water and eventually into the atmosphere. It started slowly. The first oxygen produced by cyanobacteria was absorbed almost immediately by the chemical environment it was released into. The early oceans were full of dissolved iron and other reduced compounds that reacted with oxygen as fast as it appeared, preventing it from accumulating. The rock record preserves the evidence of this phase in the form of banded iron formations, layered deposits of iron oxide alternating with silica, found in ancient geological formations in places like the Pilbara region of Western Australia and the Superior province of North America, representing hundreds of millions of years during which iron was being oxidized out of the oceans and precipitating to the seafloor as the oxygen levels in the water slowly rose. Each layer is a record of the slow, patient accumulation of a waste product that was, to most of the biosphere, a poison. Eventually, the iron ran low. The chemical sinks that had been absorbing the oxygen as fast as it was produced began to fill up. The oxygen had nowhere left to go. It began accumulating in the atmosphere. The Great Oxidation Event, as geologists call it, is dated to approximately 2.4 billion years ago, the point at which atmospheric oxygen levels became high enough to leave a clear, unambiguous signature in the rock record: oxidized continental surfaces, sulfate deposits, the disappearance of certain minerals that can only form in the absence of free oxygen, the arrival of others that can only form in its presence. The atmosphere of Earth changed in a way that was, for most of the life then existing on the planet, catastrophic. Oxygen for an anaerobic organism is not simply an unfamiliar molecule, it is an active threat. Oxygen reacts with the organic molecules inside cells, disrupting membranes, damaging proteins, breaking apart the chemical machinery that the cell depends on to stay alive. An anaerobic bacterium placed in an oxygen-rich environment does not adapt, it dies, in the same way that a human placed in an environment of pure chlorine gas does not adapt. The chemistry is incompatible with continued function. The rise of atmospheric oxygen, which in geological terms was a gradual process spanning millions of years, was in biological and evolutionary terms a change of extraordinary speed fast enough that organisms capable of evolving their way out of the problem did not have sufficient time to do so before the concentrations became lethal. The scale of the die-off is genuinely difficult to estimate because the organisms involved left no conventional fossil record. What we have are chemical signatures, genomic evidence from the lineages that survived, and indirect inferences from the rock record. The estimates that researchers have converged on, using these tools, suggest that somewhere between 80 and 99% of all life on Earth at the time died during or in the immediate aftermath of the Great Oxidation Event. The range is large because the evidence is indirect, but even the conservative end of that range is a number that dwarfs every mass extinction in the conventional fossil record. The Permian-Triassic event, the worst of the named extinctions, eliminated 96% of marine species. The Great Oxidation Event may have eliminated 90% or more of all life on Earth. And it was not caused by an asteroid. It was not caused by a volcano. It was caused by one group of organisms learning to do something metabolically useful and releasing a byproduct that their neighbors had no defense against. I want to stay with that for a moment because the strangeness of it deserves full attention. The oxygen you are breathing right now, the molecule your cells require to extract energy from glucose, the molecule without which your brain stops functioning within minutes, the molecule that makes complex multicellular life possible at all, by providing such an efficient source of chemical energy, that molecule was 2.5 billion years ago, an extinction event. It was the most destructive thing that had ever happened to life on Earth at that point in the planet's history. It arrived as a waste product. It accumulated slowly. It killed nearly everything. And then, after 1 billion years of quiet recovery, during which the surviving lineages slowly evolved biochemical machinery capable of tolerating and eventually exploiting this new atmospheric reality, it became the foundation of every complex organism that has ever lived. The recovery from the Great Oxidation Event is sometimes called, with a deadpan accuracy that planetary scientists and paleontologists clearly appreciate, the boring billion. The geological record between approximately 1.8 and 800 million years ago is, compared to what came before and after, remarkably uneventful. Life continues. Single-celled organisms carry on. But the diversity and complexity and ecological innovation that had been building in the earlier biosphere has been knocked back hard. And it takes close to 1 billion years for the surviving lineages to work their way back toward the kind of complexity that eventually produces multicellular organisms. 1 billion years of recovery. 1 billion years of quiet, patient rebuilding after life nearly ended itself by learning to breathe. The first complex multicellular organisms appear in the fossil record approximately 600 million years ago. The Cambrian explosion follows at about 540 million years ago. From that point, the diversification of animal life proceeds through all the subsequent extinctions and recoveries until the present. But the entire history of complex life on Earth, every animal, every plant, every fungus, every organism with more than one cell working in coordination toward a common biological purpose, sits on top of a foundation that was nearly destroyed twice before any of it existed, once by the oxygen that would later make it possible, once by the volcanic catastrophe that nearly ended it after it had already spent 300 million years building toward its Permian peak. The threat is real. the thread is also genuinely thin in places. There are points in Earth's history where the fossil record compresses to almost nothing, where the pages of the book go nearly blank, and what is on either side of those blank pages is so different that the continuity between them is hard to see without knowing to look for it. Life survived those compressions. Each time something held, each time some lineage in some environment made it through and carried the possibility of complexity forward into the next era. But the margins were real, the near misses were real. The biology of the survivors often bears the marks of what they survived, in the form of genetic bottlenecks, and the absence of lineages that should have been there and weren't because they did not make it across. The relevance of this to the search for life elsewhere is uncomfortable but direct. Earth is the success story. Earth is the one that worked, the one we point to as proof that planets can be alive for billions of years. And even Earth has been within reach of a permanent silence on multiple occasions. If the Siberian Traps eruption had been somewhat larger or somewhat more prolonged, if the chemical sinks had not absorbed the early oxygen long enough for some anaerobic lineages to develop tolerance, if the asteroid 66 million years ago had been somewhat larger or had struck at a different angle or had arrived 10 million years earlier, before the mammalian lineage had established enough diversity to include survivors. The contingency in Earth's own history is profound. The number of moments where a slightly different outcome would have meant no complex life here is not zero, it is not small, and Earth is the planet that succeeded. Earth is the one we know made it. What does that suggest about the planets we cannot examine as closely to ones where the window was real, but the thread may not have held through whatever their equivalent of the Great Dying was, or through whatever their version of the oxygen catastrophe was, or through whatever geological or astronomical event pushed their particular biology past the point from which recovery was possible? We have one example of life surviving its own near-extinctions. We do not know what fraction of habitable worlds produce that outcome. We know the fraction is at least 1 in whatever the total is. We do not know how much larger than 1 the numerator gets. That uncertainty is the honest place to stand. And from that place, we have to ask the question we have been approaching all night, not just whether life can survive on a planet once it gets started, but whether it gets started at all, and how often, and under what conditions, and whether the conditions we think are sufficient are actually sufficient or merely necessary. Because habitability and the actual presence of life are not the same thing. They never were, and the gap between them is the gap we have been trying to measure since the first time anyone thought to ask whether the lights were on somewhere other than here. There is a word that appears constantly in the literature on exoplanets and the search for life beyond Earth, and it does a great deal of work that it does not entirely earn. The word is habitable. It appears in headlines and press releases, and the titles of scientific papers, and the captions of telescope images. Habitable zone planet discovered. Earth-sized world in habitable zone of nearby star. Potentially habitable candidate identified in new survey data. The word is everywhere, and it carries with it a strong implication that what has been found is a place where life could exist, a place where the conditions are right, a place that is, in some meaningful sense, ready. The problem is that habitable and inhabited are not synonyms. They are not even close synonyms. They describe entirely different things. Habitable is a description of conditions of temperature ranges and atmospheric pressure, and the presence or absence of liquid water, and the chemical environment and the energy budget. It is a description of what a place allows. Inhabited is a description of what a place actually contains, whether anything showed up, whether the chemistry of non-living matter crossed the threshold into self-replicating, metabolizing, evolving biological systems, whether the potential was used. A vacant lot in a city with running water and electricity connected to the grid is habitable in the sense that a house could be built there and a person could live in it. It is not inhabited. No one is home. The conditions are present. The occupant is not. Here is what we actually know about how often the inhabited condition follows from the habitable one. We know it can happen. We are the proof that it can happen. That is the entirety of our confirmed dataset. One planet, one example. One instance of a world where the conditions existed and life appeared and continued for billions of years. From one example, you cannot derive a rate. You cannot say it happens commonly or rarely or almost never or almost always. You can only say it happened at least once. The statistics of a single event are the statistics of nothing. You need at minimum 2 data points before the concept of a rate begins to have meaning, and we do not have 2. We have 1, and we have spent decades arguing about what it implies. What we do know is something about the timing on the one example we have. Earth became capable of supporting liquid water on its surface somewhere between 4 billion and 4.4 billion years ago, depending on which geological evidence you trust and which interpretation of that evidence you find most convincing. The oldest minerals on Earth that preserve information about early surface conditions are zircon crystals from the Jack Hills of Western Australia, some of which have been dated to approximately 4.4 billion years. The chemical signatures within those crystals are consistent with liquid water having been present at the surface when they formed. That is not a direct detection of an ocean. It is an inference from chemistry. But the inference is robust and widely accepted. The earliest convincing evidence of biological activity in the rock record dates to somewhere between 3.5 and 4 billion years ago, depending on what you accept as convincing. The oldest directly imaged microbial structures, fossilized stromatolites, which are layered mats built by communities of microorganisms, date to approximately 3.5 billion years. Some chemical signatures that biological metabolism tends to produce, particularly the characteristic pattern of carbon isotope ratios that living things leave behind when they process carbon, have been detected in rocks as old as 3.8 or 3.9 billion years. Those older detections are debated. Some researchers accept them. Others argue the signals could have been produced by non-biological processes operating at high temperatures and pressures. The debate is real and has not resolved. So the gap between Earth being habitable and Earth being inhabited is somewhere between 0 and 700 million years, with the honest answer being that we do not know where within that range the actual transition occurred. It might have been fast life appearing within a few tens of millions of years of the conditions stabilizing, suggesting that the chemistry of life's origin proceeds quickly given the right environment. Or it might have been slow 700 million years of chemistry running and failing and running again before the first self-sustaining biological system finally took hold, suggesting that the origin of life is a difficult and improbable event even on a planet with everything it needs. Those two possibilities have radically different implications for how common life is in the universe. If life appears quickly given the right conditions, the universe is probably full of it. If life requires hundreds of millions of years of chemical lottery playing before it gets started, the universe might be nearly empty of it even in places where the conditions are excellent. We cannot tell which scenario describes Earth from the inside, because we do not have a clear record of the origin event itself. What we can do is think carefully about what the origin of life actually requires, and whether the requirements are easy to meet or genuinely difficult. The transition from non-living chemistry to a living cell is not a single step. It is a convergence of multiple systems, each of which has to work well enough to do its part, all of which have to be operating in the same place at the same time in a compatible way. You need an information storage system, something that can encode the instructions for building biological molecules and pass those instructions to the next generation with high enough fidelity that the instructions are preserved, but with enough imperfection that variation can accumulate and evolution can operate. On Earth, that system is DNA and RNA. Whether there are alternative chemical systems that could play the same role in a different biochemistry is a genuine open question. You need a catalytic system molecules that can accelerate the chemical reactions that biology requires, without which those reactions would proceed so slowly that no cell could maintain itself. On Earth, those are proteins, and the instructions for building proteins are encoded in DNA, creating a dependency loop that is one of the deepest puzzles in origin of life research. You need a containment system, some kind of boundary that separates the inside of the cell from the outside, maintaining the chemical environment that the cell's internal processes require, and preventing the components from diffusing away into the surrounding medium. On Earth, that boundary is the lipid bilayer membrane. You need an energy source, a way to drive the chemistry of life against the thermodynamic tendency of complex molecules to break down into simpler ones. And you need all of these things to come together in a single location in a form that can make imperfect copies of itself before it falls apart. There are scientists who have thought carefully about this problem for decades and concluded that it is extraordinarily difficult, that the probability of all these components converging spontaneously in a working configuration is so low that it might happen only a handful of times in the history of an entire galaxy, perhaps less. There are other scientists, equally careful and equally serious, who have concluded that the individual components are chemically favorable enough that they assemble readily under the right conditions, and that the full transition to a self-replicating system is essentially inevitable on any planet with liquid water, the right chemical inventory, and sufficient time. Both groups are working from the same evidence. They reach opposite conclusions. The evidence is genuinely insufficient to settle the question, and anyone who tells you otherwise is more confident than the data allows. A useful way to hold this uncertainty is the distinction between necessary conditions and sufficient conditions. A seed requires good soil to germinate. Good soil is a necessary condition for the seed, but good soil is not sufficient. You can drop a seed in excellent soil and get nothing. The seed might be non-viable. It might be the wrong species for the soil chemistry. It might germinate and then be consumed by something before it establishes. The soil might be good in every way you tested it, and subtly wrong in some way you did not think to check. Habitability is the soil. It is necessary. It is not sufficient. The seed has to actually take. And the rate at which seeds take in good soil is a question about the seeds and the specific soil and the specific conditions and the timing, not just about whether the soil is good. The universe is, by our best estimates, seeding hundreds of billions of potentially fertile plots across this galaxy alone. We do not know what fraction of those seeds germinate. We have watched one germinate. We have not been able to watch another. We do not know if the field we are standing in is crowded with growth we cannot see from where we are, or whether we are the only thing growing in a very large, mostly empty field. Both pictures are consistent with what we know. Neither can be ruled out. The honest position is not confidence in either direction. The honest is that we are at the beginning of being able to ask this question with any rigor, and we have not been asking it with rigor for long enough to have a real answer. Mars is the most painful specific case to sit with in this context. We have spent 60 years sending spacecraft to Mars, orbiters, landers, rovers, atmospheric probes. We have mapped its surface in extraordinary detail. We know the mineralogy of its rocks, the composition of its soil, the history of its water, the structure of its interior, the behavior of its atmosphere through the seasons. We know more about Mars than we know about significant portions of Earth's ocean floor, and we have found, in Gale Crater and in Jezero Crater and in the ancient rocks of the Southern Highlands, a world that had every ingredient we know of that life requires: liquid water in abundance for hundreds of millions of years, chemical energy sources in the form of hydrothermal systems and volcanic activity, organic carbon compounds, detected by curiosity in the mudstones of Gale Crater, the mineral chemistry consistent with environments where microbial life on Earth would be thoroughly at home. Mars, in the era between 4 and 3 billion years ago, was a world that had the soil. Whether the seed ever took is the question we have been trying to answer for 60 years and cannot yet answer. The sample tube at Jezero is the closest we have come to an answer, a potential biosignature in a sealed container on the surface of another planet. The most carefully selected, most scientifically significant rock sample in the history of our species, sitting in the wind, waiting. The people who drilled it are still working. The mission that would retrieve it is still being designed and funded and argued over in budget meetings and congressional hearings, and the kind of institutional processes that move slowly while rocks sit still. The late 2030s is the current estimate, possibly later. And even when it comes back, even when the laboratories of Earth get to apply their full analytical power to it, the answer might not be clean. The potential biosignature might confirm as biological under every test that can be applied. Or it might yield an abiotic explanation that satisfies the skeptics. Or it might sit in a middle ground of ambiguity that requires additional samples from additional locations to resolve. Science does not always produce clean endings. Sometimes it produces better questions. Venus is the case we will probably never resolve at all. If life existed in Venus's oceans during its 2 to 3 billion years of habitable conditions, the evidence of that life has been erased with a thoroughness that approaches completeness. The surface of Venus today is a high-temperature, high-pressure, chemically active environment that has been operating at those conditions for 700 million years. Whatever organic molecules might have been preserved in Venusian sediments from the habitable era have had 700 million years of heat and pressure and chemical reaction to work on them. The preservation potential is essentially zero. There are proposals for atmospheric missions that could float in the cloud layers of Venus at altitudes where temperatures and pressures are closer to Earth-like conditions, and there is speculation that microbial life might conceivably survive in those cloud layers today, extracting energy from the chemical gradients in the atmosphere. But those are speculative searches for present life in a marginal environment. The historical record of whatever Venus's oceans might have contained is gone. And then there are the worlds we have not talked about yet. In this context, the ones in our own solar system that are not planets in the conventional sense, but that have nonetheless produced environments where the basic requirements for life as we understand it are present. Europa, the second of Jupiter's 4 large moons, has beneath its icy surface an ocean of liquid water that by current estimates contains more liquid water than all of Earth's oceans combined, kept liquid by the tidal heating generated as Jupiter's enormous gravity flexes the moon's interior. The ocean has been liquid for a very long time. It is in contact with a rocky seafloor, which means the kind of hydrothermal chemistry that is associated with some of the most ancient and robust microbial ecosystems on Earth may be operating there right now. Enceladus, a small moon of Saturn, is actively venting water vapor and ice particles from its south polar region through cracks in its surface, driven by an internal liquid ocean that is not merely suspected but confirmed by the chemical analysis of those plumes conducted by the Cassini spacecraft before it was deliberately crashed into Saturn in 2017. The plumes contain water, organic molecules, molecular hydrogen, the last of which is a specific indicator of hydrothermal reactions occurring at the interface between liquid water and hot rock. Titan, Saturn's largest moon, has a thick nitrogen atmosphere, complex organic chemistry in its atmosphere and on its surface, and lakes and seas of liquid methane and ethane on its surface that some researchers have proposed as a potential environment for a form of chemistry that could, in principle, support a biology utterly unlike anything on Earth, one that uses liquid methane as a solvent the way Earth life uses liquid water. These are real places. They are in our solar system. They are reachable in principle with spacecraft and patience and sufficient funding. The Europa Clipper mission launched in October of 2024 and is currently en route to Jupiter, expected to arrive in 2030 and conduct dozens of close flybys of Europa to characterize its ocean and assess its habitability in detail. A Dragonfly mission to Titan is in development, a rotorcraft lander that would fly between surface sites, examining the organic chemistry of Titan's surface. These missions are real. The science they will return is real. But they will not tell us definitively whether life exists in Europa's ocean or Titan's methane seas. They will tell us whether the conditions are there. Whether anything is using those conditions is a question that landing on the surface and drilling into the ice and examining what comes up would begin to answer. Those missions are further away in time and much further away in cost. Beyond our solar system, the tools available to us narrow dramatically. We cannot send anything there in any time frame that means anything to the civilization doing the sending. The nearest star system, Alpha Centauri, is 4.2 light-years away. The fastest spacecraft humanity has ever launched, the New Horizons probe, is traveling at approximately 58,000 kilometers per hour. At that speed, a journey to Alpha Centauri would take approximately 78,000 years. The fastest theoretical propulsion systems currently under serious research consideration might reduce that to a few decades, but only for tiny, sail-like probes carrying no humans and returning no samples. The era of physically visiting another star system's planets is not on any realistic horizon. For exoplanets, our toolkit is limited to what we can learn from light. The James Webb Space Telescope, operating since 2022, has demonstrated that it can measure the atmospheric composition of certain exoplanets by analyzing the specific wavelengths of starlight that are absorbed or transmitted as the planet passes in front of its host star. The technique is called transmission spectroscopy, and it works by comparing the star's spectrum with and without the planet in front of it. The difference tells you which molecules are present in the planet's atmosphere. JWST has already produced atmospheric detections for several exoplanets, including detections of carbon dioxide, water vapor, methane, and sulfur dioxide in various planetary atmospheres. The coming generation of extremely large, ground-based telescopes, with primary mirrors measuring 30 to 40 meters in diameter and adaptive optics systems capable of correcting for atmospheric distortion in real time, will push this capability significantly further, potentially allowing the detection of biosignature gases like oxygen and ozone in the atmospheres of rocky planets around nearby stars. What none of this can do is confirm life. Detecting oxygen in a planet's atmosphere is suggestive, because oxygen is chemically reactive and tends to be consumed rapidly unless something is continuously producing it, and on Earth, the thing producing it is photosynthesis. But there are abiotic processes that can produce oxygen in a planetary atmosphere, and distinguishing biological from non-biological oxygen production from light years away is a problem that requires multiple overlapping measurements and careful modeling, not a single detection. Detecting methane alongside oxygen is more suggestive, because those two molecules react with each other and should not coexist in a planetary atmosphere in equilibrium unless something is continuously replenishing both of them, and on Earth the things doing that replenishing are ecosystems. But again, the inference is probabilistic, not certain. There is a thought experiment that helps clarify the position we are in. Imagine an astronomer on a planet orbiting a star 300 light-years from Earth. They have excellent telescopes. They have been studying our solar system from their distant vantage point for the last few years of their civilization's scientific history. They can detect all 8 of our planets from the periodic signals they create in our sun's motion and brightness. They can measure Earth's atmospheric composition through transmission spectroscopy as Earth passes in front of the sun. They detect oxygen, water vapor, methane, ozone, nitrous oxide, a combination of molecules that their models identify as almost certainly biological in origin. They publish a paper. They put Earth on their candidates list. They give their colleagues conference presentations about the intriguing atmospheric signatures of the third planet in the solar system of the nearby G-type star. What they cannot do is come here. The distance is too large. The journey would take longer than their civilization has existed. They cannot send a probe that returns data in any useful time frame. They cannot collect a sample. They will know, with high probability, that something biological is happening on Earth. They will never know what. They will never see a tree, or an ocean, or a city. They will hold Earth in their catalogue as a compelling positive result and spend the rest of their scientific history unable to follow it up in any direct way. That is the position we are in with every candidate exoplanet we will ever identify. We will compile lists. The lists will grow as the telescopes improve and the surveys expand. Some of the entries on the lists will represent genuine biosignatures. Some will be false positives generated by abiotic chemistry we have not fully modeled. We will rarely have the means to determine which is which. The Mars sample tube is the closest we will ever come to a definitive answer about any world beyond our own, and it is sitting unretrieved on a planet we have been visiting with robots for 60 years. Everything beyond Mars is a light signature, a spectroscopic measurement, an inference from chemistry we observe at the distance of years. The sample is the high water mark. The light is everything else. And the light, as it turns out, does not show us the universe as it is, it shows us the universe as it was. The difference between those two things is not trivial. It is, in fact, one of the most fundamental and least intuitively absorbed facts about the cosmos we live in. The sky you see when you step outside at night is not the sky. It is a record. And the record was written at many different times by many different sources, and some of those sources no longer exist in the form that wrote it. That is where we have to go next. When you step outside on a clear night and look up at the stars, you are not seeing the sky. That sentence sounds like a poetic overstatement, the kind of thing someone says to sound profound before explaining something that turns out to be less interesting than the setup promised. It is not an overstatement. It is a precise physical description of what is actually happening when light from distant objects enters your eye. You are not seeing the sky as it currently exists. You are seeing a record. A collection of signals that left their sources at many different times, traveled at the only speed that information can travel through the vacuum of space, and arrived at your eye simultaneously at this particular moment, giving the false impression of a single coherent scene existing all at once. The sun you see during the day is 8 minutes and 20 seconds old. The light hitting your eyes left the solar surface 8 minutes and 20 seconds ago. If the sun were to somehow disappear at this instant, you would not know for 8 minutes and 20 seconds. You would continue to see it, continue to feel its warmth, continue to navigate by its position in the sky for 8 minutes and 20 seconds after it had ceased to exist. The moon is a little over 1 second old when you see it. The nearest star to the sun, Proxima Centauri, is 4.2 light-years away. The light you see from Proxima tonight left it approximately 4 years ago. Whatever Proxima is doing right now, at this literal instant, will not reach Earth for another 4 years. The information about the present state of the nearest star in the universe is 4 years behind schedule. Sirius, the brightest star in the night sky, is approximately 8.6 light-years away. The light from Sirius entering your eye tonight left it around the same time as a specific moment in your personal history approximately 8.5 years ago. Whatever you were doing then, whatever was happening in the world at that time, that is when the photon you are currently receiving departed. Polaris, the North Star, which navigators have used for orientation for thousands of years, sits approximately 430 light-years away. The light from Polaris that you see tonight left the star sometime in the early 17th century. Galileo Galilei was alive when that light began its journey. He may have been looking up at the same star, receiving light that had left it around the time of the late medieval period. The light you receive and the light he received are from different eras of the same star's life, separated by 4 centuries. The stars visible to the naked eye on a dark night span range from a few light-years to several thousand light-years in distance. The faintest ones you can pick out with good eyes, under good conditions, are sending light that has been traveling for thousands of years. Light that left its source before the construction of the pyramids in some cases, before the invention of writing in others. When you look at the band of the Milky Way stretched across the sky on a sufficiently dark night, the central concentration of light you are seeing is the combined glow of billions of stars in the galactic core, and that light left its sources approximately 26,000 years ago. 26,000 years ago, the anatomically modern humans who looked up at the same galactic band had not yet developed agriculture. They had not built cities. They had not invented writing or mathematics or any of the technologies that we associate with civilization in any form. The light from the galactic center that fell on their eyes was light that had left 26,000 years before them. The light from the galactic center falling on your eyes now left 26,000 years before you. The two of you are receiving transmissions from the same source, separated by the entire span of recorded human history, and neither transmission tells you what the galactic center looks like today. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is approximately 2.5 million light-years away. It is faintly visible to the naked eye, on a very dark night, as a smudged oval of light, slightly larger than the full moon, but enormously fainter. The light forming that smudge left Andromeda 2.5 million years ago. At that time, the genus Homo had only just appeared on Earth. Our earliest ancestors who could be described as human in any meaningful taxonomic sense were alive when that light began its journey. The light has been traveling for the entire span of human evolutionary history and arrived tonight. The Andromeda Galaxy, as it exists right now, at this moment, as you look at it, will not be visible from Earth for another 2.5 million years. What you see is a 2.5 million year old photograph of a galaxy that by now has had 2.5 million years of additional history that you cannot see. The James Webb Space Telescope has imaged galaxies at the edge of the observable universe, objects whose light has been traveling for more than 13 billion years. The universe itself is approximately 13.8 billion years old. The most distant objects JWST has detected sent their light when the universe was less than 5% of its current age. The galaxies that produce that light have since had 13 billion years of evolution, star formation, stellar death, mergers with other galaxies, possible development of planetary systems, and everything else that happens to galaxies over the course of their lives. Whether those specific galaxies still exist in recognizable form, whether the stars within them have lived and died and been replaced by new generations of stars, whether any of the planetary systems in those galaxies had their habitable windows open and closed in the intervening 13 billion years, none of that is visible to us. We see the infants. We cannot see the adults they became. The sky, in other words, is a postal system operating at the only delivery speed available to it, which is the speed of light, and delivering mail that was sent at many different times by many different senders. When you look up at a dark night sky and see several thousand stars with the naked eye, you are opening a mailbox that contains letters mailed at different points across thousands of years of cosmic history. Some letters were mailed recently in astronomical terms. Some were mailed long before the Roman Empire existed. Some were mailed before any human civilization had begun. They all arrived in your mailbox tonight because the delivery time, the distance divided by the speed of light, happened to work out to the same value of right now for each of them. The simultaneity of their arrival is an artifact of geometry, not an indication that the senders sent them at the same time. Some of those letters were sent by senders who no longer exist. Stars D, not frequently in human terms, not in ways that produce noticeable changes in the night sky on timescales that human civilizations can observe without careful measurement, but constantly in the context of galactic history. Small stars like red dwarfs, as we discussed, will burn for trillions of years. Medium stars like our Sun will live for approximately 10 billion years before exhausting their hydrogen fuel and transitioning to a red giant phase and eventually collapsing into a white dwarf. Massive stars, the ones that burn brightest and are visible at the greatest distances, live fast and die violently. The most massive stars spend only a few million years on the main sequence before their cores collapse and they explode as supernovae, briefly outshining entire galaxies before fading into neutron stars or black holes. The timescales vary enormously by mass. The principle is universal. Every star has a finite life. Every star will eventually become something other than what it currently is. There are stars in the night sky that ended sometime in the last several hundred years. The light from those stars, the light from the stars themselves in their living form, is still arriving at Earth because the distances involved are large enough that the news of their death has not yet reached us. The star has been gone for decades or centuries. The light it emitted before it died is still in transit, will be in transit for years or centuries more, arriving at Earth and being seen as a star by anyone looking up, even though the star itself is gone. You cannot tell which stars those are by looking. The living stars and the light from the recently dead stars look identical from here. The envelope does not say when the letter was written. It says only where it came from and how bright the source was. There is something in that fact that goes beyond the astronomical and into something harder to name. The night sky contains, mixed in among the living stars, the last light of stars that have already died. The memorial and the living are indistinguishable to the naked eye. You are looking at both simultaneously without being able to tell them apart. The sky is partly a view of the present and partly a view of a past that no longer exists in the form that generated it, and you cannot draw a line between the two portions from where you stand. Now extend that thought to planets, to habitable planets, to worlds where life may have existed. The light from a planet around a star 50 light-years away is 50 years old when it reaches us. The atmospheric composition we would measure in that light, the oxygen levels, the water vapor content, the methane concentration, the presence or absence of the molecular combinations that suggest a biosphere, is the atmospheric composition of 50 years ago. A planet around a star 100 light-years away, 100 years out of date. A planet around a star 1,000 light-years away, 1,000 years out of date. For nearby stars, those timescales are short enough that they do not change the picture significantly. Planetary atmospheres evolve slowly. A few decades or centuries of lag does not meaningfully alter the conclusion you draw about whether a world is habitable or inhabited. But civilizations do not evolve slowly. Civilizations rise and collapse on timescales of hundreds to thousands of years. The entire span of recorded human history is approximately 5,000 years. Modern technological civilization, the kind that produces detectable electromagnetic signals and atmospheric modifications that could be identified as technological in origin, is approximately 200 years old. If there were a planet 1,000 light-years away that had developed a technological civilization, and that civilization existed for 500 years and then collapsed, whether from war or disease or resource depletion or simple cultural transformation into something that no longer produces detectable signals, and if that collapse happened 800 years before the light we are currently receiving left the planet, we might be looking at the light from an era when the civilization was at its peak. We would see the signatures. We would add the world to the candidates list. The civilization would have been gone for 800 years. We would have no way of knowing. The concept of now, applied across interstellar distances, loses its meaning in a way that is not philosophical but physical. Einstein's theory of special relativity tells us that simultaneity is relative, that the question of whether two events separated in space happen at the same time has no absolute answer, only answers relative to specific reference frames. For practical purposes, and at the speeds and distances of everyday human life, this does not matter. But at cosmic scales, the absence of a universal now is not an abstraction, it is the actual structure of the universe. When we ask whether there is life out there right now, we are asking a question that has no well-defined answer in the way we mean it. We can ask whether there was life out there at the moment a given light signal left a given planet. We can ask whether there was life out there in the era whose light is currently reaching us. We cannot ask whether there is life there now in any operationally meaningful sense, because the now of a planet hundreds of light years away is a concept that our instruments and our physics cannot access. This reframes the silence we hear from the universe in a way that is both clarifying and disquieting. When we point our radio receivers at the sky and detect no structured electromagnetic signals from other civilizations, we are not detecting the absence of civilization across the universe at this moment. We are detecting the absence of signals that were sent close enough in the past and in a direction aimed at us with enough power to be detectable by our current instruments. A civilization that existed 500 light-years away and sent radio signals for 200 years and then stopped, whether by extinction or by transition to communication methods we cannot detect, would have a shell of radio waves expanding outward through space at the speed of light. Whether that shell has reached Earth yet depends on the geometry and the timing. Whether we were listening when it passed depends on when we developed radio astronomy. The window of overlap between their transmission and our reception might be very small, might be zero, might have already passed. We would not know. The silence is real. The silence is also not proof of the thing it is most often taken to mean. It is not proof that no one ever spoke. It might be proof that the moments of speaking and the moments of listening did not overlap, that the envelopes got mislaid, that the post arrived after the recipient moved, that the signals were sent in languages our instruments are not designed to receive, that the civilizations that sent signals have been dark for thousands of years, and their signals have already passed through our neighborhood before we had ears to hear them. The silence has many possible explanations. The simplest one, that no one is out there, is among them. But it is not the only one, and it is not necessarily the most likely one when you account for the physics of information moving at the speed of light through a galaxy 13 billion years old. The picture that emerges from all of this is not the picture of an empty universe or a populated one. It is something more specific and more strange. It is a picture of a universe full of moments. Each star system with its planets is a moment, a specific window of time during which conditions of a particular kind exist. The window opens, the window runs, the window closes. The length of the window varies. What happens inside the window varies. Whether anything appears inside the window to take advantage of the conditions varies, and the light from each window travels outward in all directions at the speed of light, carrying information about what the window looked like at the moment the light left it, forever. The universe is not a place where things exist. It is a place where things happened, and the record of what happened is traveling in all directions forever at the speed of light, accumulating in the detectors of anyone anywhere with the instruments to receive it. We are receivers. We have been receivers for a very short time compared to how long the signals have been traveling. We are opening mail that has been in transit for billions of years and trying to read it with instruments that have existed for decades. The mail keeps coming. Most of it we cannot yet read. Some of it we are beginning to decipher. None of it tells us about the present state of the sender, only about the state of the sender at the moment of sending. And some of the senders, by the time their letters arrive, are no longer there. That is the actual texture of the search for life in the universe. Not a radio dial we are slowly tuning toward the right frequency. Not a telescope we are slowly pointing toward the right star. A mailbox that has been filling for 13 billion years, that we have only just begun to sort through, containing letters from senders at every stage of existence and non-existence, arriving at our door in an order determined entirely by distance and the speed of light, with no indication on any envelope of whether the sender is still home. We sort through them. We do our best. We make our maps of the signals and the candidates and the potential biosignatures and the interesting atmospheric compositions. The maps are real and they are useful, and they are the best thing we have. The maps are also fundamentally maps of the past, drawn from light that left its sources before any of the map makers were born, describing places that may or may not still exist in the form the light suggests. We hold those maps and we look at them and we try to figure out what they mean about the universe as it is right now, in the only now that is available to us, which is the now of this planet, this moment, this particular evening in the long habitable window of a world that is demonstrably past the middle of its own story. That is where we have spent this entire night arriving, not at the question of whether anyone is out there, at the question of where we are in the story, at the question of what it means to be inside a window that is open, knowing that windows close, reading letters from windows that have already closed, trying to determine whether any other windows are open right now in the only now we have access to. And that question, the question of where we are in our own story, is the one we have to look at directly before we can close the night honestly. There is an instinct, when you have spent time thinking about dead worlds and closing windows and the long silence of a universe full of moments that have already passed, to position Earth as the exception, the one that worked, the outlier, the planet that by some extraordinary combination of circumstances avoided everything that Mars and Venus could not avoid, threaded the needle of every extinction event, maintained its magnetic field and its oceans and its atmosphere through 4 billion years of geological and astronomical turbulence, and arrived at the present moment with its biosphere intact, and a species on its surface capable of reconstructing the entire history of how it got here. The instinct is to feel, even if you do not consciously articulate it, that Earth is not on the same list as those other worlds, that Earth is in a different category, that the story of Earth is a story of permanence in a universe of impermanence. Earth is on the same list. Earth has always been on the same list. The difference between Earth and Mars is not categorical. It is not structural. It is not the difference between a world built to last and a world built to fail. It is a difference of timing and circumstance, and the specific sequence of events that played out on each world across billions of years. Mars lost its magnetic field. Earth has not lost its magnetic field yet. Venus tipped into a runaway greenhouse. Earth has not tipped into a runaway greenhouse yet. The word yet is doing real work in both of those sentences. Earth is not in the morning of its habitable era. It is not even at noon. The numbers are specific, and they have been carefully derived by multiple independent lines of research, and they point in the same direction. Here they are, laid out plainly, without softening. Earth formed approximately 4.5 billion years ago. Liquid water has been present on the surface for somewhere between 4 and 4.4 billion years. Life has been present in some form for approximately 3.5 to 4 billion years. Complex multicellular life has existed for approximately 600 million years. Animals with recognizable body plans have been around for approximately 540 million years. Our own genus, Homo, appeared approximately 3 million years ago. Our species, Homo sapiens, approximately 300,000 years ago. The agricultural revolution, the transition from hunter-gatherer subsistence to settled food production that initiated everything we recognize as civilization, approximately 12,000 years ago. The Industrial Revolution, the beginning of the technological era that produced the instruments we are using to read the night sky, approximately 250 years ago. Modern space exploration, the era in which we have been able to directly examine other planets, approximately 65 years ago. That is where we have been. That is the full span of Earth as a living world, compressed into a list that takes 30 seconds to read. 4 billion years of biology, 300,000 years of our species, 12,000 years of civilization, 65 years of space exploration. Now look forward. The sun is brightening at approximately 10% per billion years. It has been brightening throughout Earth's entire history. The carbon cycle and the water cycle and the geological processes that regulate Earth's climate have so far compensated for the increasing solar energy by gradually reducing the atmospheric greenhouse, keeping the surface temperature within the range that liquid water requires. That compensation has limits. The models that study Earth's long-term climate future, the ones that incorporate the brightening sun and the feedbacks of the carbon and water cycles and the evolving chemistry of the atmosphere, converge on a conclusion that is consistent across research groups and has not changed significantly in its broad outline for several decades. Somewhere between 1 billion and 1.5 billion years from now, the inner boundary of the Sun's habitable zone will have moved outward to Earth's orbital distance. The compensation mechanisms will have reached their limits. The surface will begin warming in a self-reinforcing way. Water vapor will begin accumulating in the upper atmosphere faster than geological processes can remove it. The oceans will begin, slowly at first and then faster, losing water to the same mechanism that stripped Venus bare: ultraviolet dissociation in the upper atmosphere. Hydrogen escape to space, the gradual dismantling of the molecule that has covered 70% of this planet's surface for 4 billion years. The end of complex multicellular life on Earth is not an event that happens on a specific date. It is a threshold that is approached gradually as conditions change. The threshold is not the same for all organisms. Microbes, particularly the extremophiles that already live in environments that would kill almost everything else in the superheated water of deep ocean hydrothermal vents, in the chemically extreme brines of hypersaline lakes, in the rock itself, kilometers below the surface may persist for hundreds of millions of years, past the point where surface conditions have become untenable for animals and plants. But the kind of world we know, the world with forests and oceans and weather and seasons and animals and the food webs that connect them, has a window that is shorter than the microbe's window by several 100 million years. 1 to 1.5 billion years. That is the remaining duration of Earth's habitable era for complex life by the central estimates of the best current models. The planet has been habitable for complex life for approximately 600 million years. It will be habitable for complex life for approximately 1 to 1.5 billion more years. The total window for complex multicellular life on this planet From the Cambrian explosion to the point where the sun's increasing energy makes it untenable is somewhere between 1.6 and 2.1 billion years. We are approximately 600 million years into that window. We are not at the beginning. We are somewhere between a quarter and a third of the way through. The largest portion of Earth's habitable era for complex life is ahead of us, not behind us, if you measure from the Cambrian, but the planet's total habitable era, including the 4 billion years of microbial life before complex